So today we're going to talk about a different type of launch, basically using a big gun instead of a gigantic rocket. So let's talk for a second about what getting to orbit means. In order to get to orbit, a rocket has to do a bunch of different things. So it has to get up to altitude and it has to get going at orbital speeds, which means that it has to be going very, very, very fast. That drives the rocket to be just humongous. So the Electron, which is the launch that we're watching right now, is one of the smallest rockets that's been made for orbital insertion. It takes about 300 kilograms to low Earth orbit, and it weighs about 13,000 kilograms. So of the total mass of the rocket, only 2.3% is the actual payload. So you're basically using all of this fuel and rocket mass to launch a very, very small thing into orbit. The question is, can we actually do better? Is there a different way? One of the ideas is build an entire system on the ground. So we can accelerate an object to orbital speeds using some sort of a device on the ground. Then you don't have to lift the fuel with the rocket. That would save a huge amount of weight on the rocket because you don't have to launch any fuel at all. You're doing all of the acceleration on the ground. System would be completely reusable because you basically launch something, you reset the system, you launch something again. You don't have to fuel up the rocket or do anything like that. And that would drive launch costs down significantly. Question is it really possible to do such a thing? One idea that people have is to use a big gun to do this. So back in the 1960s, there was this program that was called the High Altitude Research Project, or HARP. And it ran from about 1962 to 1967. And it was led by this guy named Gerald Bull. He was a Canadian citizen and sponsored by the Canadian government and the US government. And back in the 60s, there was a lot of money being spent on launching stuff into space. And so this was one of the ideas that was put forward and given a significant amount of money to explore. And so they basically took this big gun idea and ran with it. The diameter of the gun was about 16 inches, and they expanded the barrel, so they just added more length to the barrel to accelerate the payloads. The reason that they needed to expand the barrel longer is the gases expand, and the gases expanding accelerate the object. And then if you make the barrel longer, then you can accelerate the payloads for a longer amount of time. They put 3 of these big guns in, and one big gun was put into Barbados, and then they put one in Quebec, and they put one in the United States at the Yuma Proving Grounds in Arizona. And basically what they tried to do was they wanted to take these big bullets, if you will, and launch them up into the upper atmosphere and take some measurements and stuff like that. Martlet 1 was basically just used for concepts. So can we get things launched up anywhere? And so they did that and it worked. Martlet 2 was basically the main one that was used. And then Martlet 3 was supposed to have some sort of a solid engine to provide thrust. So basically you shoot it up and then the engine comes on and then it could accelerate up to orbital speeds. And then Martlet 4 was supposed to have a liquid engine to actually get to orbit. Let's talk about Martlet 2 for a little bit. There was 33 launches from the Yuma gun in 1966. And the muzzle velocities of those reached about 2,150 meters per second. And that's nowhere close to orbital speeds, but it's enough to get it up to about 180 kilometers in altitude. So it went way, way up in the air. The gun was about 120 feet or 36 meters long. So if you go from 0 to 2,150 meters per second in 36 meters of space, that is 6,500 Gs of acceleration. That is a lot of acceleration. It reached a peak of about 180 kilometers, like I said, and they took scientific data. So it actually proved that this type of thing could be useful. So the Martlet 3 and 4 series was basically to get the initial velocity from the gun, and then you get to a high altitude, and then you could actually turn on the engine of the rocket and then accelerate up into orbital speeds. So the M3, the Martlet 3, was going to take about 20 kilograms to about 500 kilometers altitude. So it would go about 3 times higher, roughly 3 times higher in altitude than the Martlet 2. And then the Martlet 4 was supposed to take about 25 kilograms to orbit. There were problems with this because, like I said, the 6,000 Gs of acceleration, things just can't endure 6,000 Gs of acceleration. Solid fuels have to be packed into a certain geometry and everything. And once you start accelerating them at 6,000 Gs, those fuels actually distort and it makes it so they don't fire anymore. And so that really complicated things. And so they never were able to get the Martlet 3 to light with a solid fuel. Then HARP was canceled. It was canceled in 1966 and 1967, and there were lots of reasons why. But, we were spending a lot of money on the Vietnam War. There was a lot of money being spent on a lot of different space technologies, but NASA's budget was being ratcheted back in the late 60s. And so this is one of the programs that was canceled. The Canadian government actually pulled out first, and the US government pulled out soon after that. So what happened to Gerald Bull? Well, he started this thing called the Space Research Corporation, and he became an international artillery consultant. And so he basically helped people build big guns. He developed new large guns for different governments. And that led him to be an arms dealer. So in the late 70s, he started selling arms to South Africa, which was not good. He spent some time in a US jail, and he was fined by the Canadian government for doing these types of things. Then he decided to ratchet things up a little bit. So in the 1980s, he worked on several very large gun designs, and then he worked with Iraq to help them build their long-range Scud missiles, which was definitely something that the United States really did not want. And so he died on March 22nd in 1990 in Brussels. So then later on, this thing called Super HARP, or SHARP, was put forth, and that was started in 1985, and they did a test firing in 1992, and it used pressurized gas to accelerate objects and not gunpowder. The barrel was 155 feet long, 47 meters in length, and John Hunter actually was the driver of this project. So the goal was to launch objects up to orbital speeds. And he wanted to get about $1 billion to build facilities to actually do this, and wanted to do this on the side of a mountain. And they never got the full funding for this. And so it was canceled before it really got going. Now there is this company called Spin Launch, and it was started in the 2020s. And the idea with Spin Launch, as you can see from this video, is to accelerate an object to very high speeds in a circle. And then as it gets accelerated up to higher and higher and higher speeds, you let the object go at exactly the right time, and it continues on in a straight line, and it will go up to orbit. That's the general idea. There is a problem that if you want to launch this thing at 7,600 meters per second and you only have a 20-meter radius, the payload would experience about 300,000 Gs as it goes around in this circle. They would need to solve a lot of technical issues to actually get this working. Then there's an idea of electromagnetic accelerators. Basically, you use magnets and electric fields and currents and stuff like that to accelerate things instead of using gases. And so this is already used to accelerate things to pretty high speeds. So roller coasters use this. Aircraft catapults use this to accelerate aircraft. And then guns actually use this too. They're called rail guns. So the general idea is that you use a magnetic object in a barrel, and then you use electromagnetics to pulse them in sequence that accelerates the object out. And so this roller coaster, which happens to be one of my favorite roller coasters, which no longer exists, called the Wicked Twister at Cedar Point, actually uses this. So you might fast forward through this if watching videos of roller coasters makes you dizzy. It basically takes and just shoots you forward. You go up, it comes down, and then it shoots you backwards. And then as you come back forwards, it shoots you forwards again. And so you're getting accelerated the entire time as you go through the straight part. And so on the part where you're actually going flat is where you do all the acceleration, which is totally different than all other roller coasters, which is super cool. But that's the idea of using electromagnets to accelerate things. So there are some big problems with big guns. Once the object leaves the barrel of any gun, it experiences air resistance, and that rapidly decelerates the object and leads to massive, massive heating. One idea that has been suggested is that you build it on the side of a mountain, like on the side of Mount Denali or on Mount Everest or something. Those are sort of unrealistic ideas because it would cost a huge amount of money to actually do that. And it would involve like governments giving up rights to mountains and stuff. I don't think that that would actually happen. The length of the barrel needs to actually be very, 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 very long, or the accelerations have to be just astronomically huge. And that limits what objects can actually be launched. So then, in summary, accelerating objects to orbital speed using ground-based mechanisms is really innovative and exciting. It was developed in the 1960s. And it's still being worked on today. People still see that goal and still are trying to achieve it. So the initial developments of these are very, very expensive, but you can reuse them over and over and over. So it makes the launch cost per orbit relatively cheap. There are a lot more new technologies that offer some hopes, but it's still a long ways off. So the initial speed, it's very doubtful that we'll ever reach orbital speeds on the ground because of this whole issue with the drag force and everything. And the fact that, if you're trying to go through the atmosphere with orbital speed, you're really going to create like plasma plumes and heat up the rocket and everything to very, very high temperatures. So probably you'll get an initial speed and then you'll use something like a rocket engine to actually get you to orbit. Getting that initial speed involves a massive, massive acceleration to get it up to speed, and then a massive deceleration due to the air resistance. So we have to figure out how to get through that. And then the length of the system needs to be very, very, very long for non-insane accelerations. And you'll see that in the mathematics video.